Welcome to this tutorial. In this video, we go through Aspen simulation of a simple ideal Rankine cycle. We start with an example. Consider a steam power plant operating on a simple ideal Rankine cycle. We assume that the steam enters the turbine at 15 megapascal and 600 degrees C, and then it's condensed in a condenser with a pressure of 10 kilopascal. We want to determine the thermal efficiency of this cycle. The steam flow rate is 10,000 kilogram per hour. So we have the boiler pressure, the steam that enters the turbine, pressure and temperature. We have the pressure in the condenser. So having this information, we can start to do our simulation. So we start the program, Aspen program. I use Aspen 12.1 version. So when you open the program, then we press on a new simulation. So you click on new simulation. And then after that, the program starts. Here you see left bottom. Here you see 4 sections or 4 bars: properties, simulation, safety analysis, and energy analysis. We always need to start with the properties part. You see these red circles on the left sidebar here. These red circles show the uh, sections in which you need to insert the needed information for the program in order to be able to do the simulation. We need to start with the specification. In a specification and then component section, you need to add the chemicals that are involved in this simulation. We have pure water, so it's not very complicated. We just add water. You have 3 options for the search here: begins with, contains, and equals. So if you select contains and then you press on find now, then you will see a list of different components given here in the database of Aspen program. So if you search for the chemical equation, here is the pure water that we are aiming for. So we just select it, or double click here, or add on, or press on this add selected compound. The compound is added. So you press close, and then since we assume that we only have water, we are good. So the next section is method section. You can either click here to find it, or you can press next. This next help you to go to the next uh, section that you need input for the program. There is one more here as well. It does these two bottoms. They are doing the same thing. So you press on the next, and then you're navigated to the method section. In method sections, you need to provide the information for the Aspen. As this in this simple simulation that we have, it's only water, so you have steam tables. That would be enough. The method filter should be a common option. The free water method should be steam table. Here, the method name, again, you can choose the steam table because, as I mentioned, we are not dealing with other components, so steam table should work fine. Then you see this red circle is a blue check now, which means that you have all the information that you need. Now, when you are done here, so when you click on the next button, a message appears. It says Run Property Analysis. The program needs to read all the information from the database and make a property analysis before you enter to the simulation environment. So we simply press on OK, and then wait a few seconds. Here it says that the table generation completed, results available. So now we are done in the properties section, and we can proceed and go to the simulation part. And now we are ready to move on to simulation. So you press on simulation. So you will be navigated to the main flow sheet. In the main flow sheet, you can add the components of your simulation and, of course, the material and energy streams. Here down to the main flow sheet, you have a section with different list of different components. If you remember, we have a turbine, we have a condenser, we have a pump, and a boiler, right? So first we need to add the turbine. So when you want to add the turbine, you need to check the pressure changers. In the pressure changers, second option here is compressors and turbine. So you click on this arrow, and this icon is for the turbine. So when it's selected, you see it's white, and then when you move the cursor to the main flow sheet, you see a plus sign here. So when you click on the main flow sheet, that block is added. So if you want to add more blocks, you just simply click several times in the flow sheet. Since we have only one turbine for now, one would be enough. If you by mistake add more than one turbine that is needed, you simply go here to cancel the insert mode, because we are in the insert mode. So you click on this arrow. Now you're in the insert mode. So you just select the component that you have added wrongly, and then you click or press the bottom delete button on the keyboard, so that will be deleted. Uh, you can rename the component by either double clicking on the name. B1, B stands for block. Here we have the turbine. So we write turbine. You have limitation for the number of characters that you can use for the name of the component. So you should be aware of that. And then you press enter, the name is added. The alternative is that you right click on the component, and then you select to rename block. You can also move the name of the block wherever you want. Then after the turbine, we have a condenser, and the condenser is an exchanger. This is not a detailed simulation, so we just are concerned about mass and energy balances. So I go for the simplest option, which is a simple heater, and we put it here as the condenser. And then the next component is pump. Again, pressure changers. You have the pump, so you put the pump afterwards. And after the pump, you have boiler. Again, this is simple simulation, so we go for exchanger and just put a simple heater here, like this. Uh, Now it's time to connect these blocks. So you need to select the material mode here, down here. So I select material. You have also heat and work. So when you click on material and it's activated, so when you go to the flow sheet, you see that on each block, you will see two red arrows. It's input and output, and a blue arrow depending on the equipment is different. So for instance, for turbine, it's water decant. So I just click somewhere in the flow sheet to start the stream, and then I move the cursor on the red arrow. When it's on the red arrow, it says feed required, so I click one more time, and this is connected. Then the output of the turbine should go to the input of the condenser. The output of the condenser goes to input of the pump. Output of the pump goes to the input of the boiler, and output of the boiler should go back to the turbine, but we just leave it like this in the main flow sheet. We don't need to close the cycle for now. So now I'm done with the streams. So I deselect the materials by clicking on this arrow. Now I can move this stream or components just by drag and drop wherever I want, and then I can rename each component and a stream. To rename a streams, you either double click here and rename it, or you right click and pick the rename option. I will do this and then we continue. Now I have added all the components, rename all the components and the streams, and we are ready to proceed. In order to proceed, as I mentioned, you can press on the next button, or you can use this left sidebar. I press on the next button, so we go to the next input needed for the program. So when you press next, then you are navigated to turb in. Turb in is the steam that enters turbine. If you remember, we said that the temperature is 600 degrees C and the pressure is 15 megapascal. So we change the units here. It's bar. We should change it to megapascal. Then we need also some information about the total flow rate. The total flow rate is given based on the mass in kilogram per hour, and it's 10,000. So this is the information that we have. We also need to make the composition inserted here. So we have several options in the drag down list here. You can either go for mass flow, mole flow, mass fraction, whatever. If I choose, let's say I choose mass fraction, if you use mass fraction, and since we have pure water is 100% water, so the mass fraction of the water is 1. If you have different fractions, then you can change it here. Now we see the red circle is a blue check now, so we are done in this section. So we move on to the next part. This is the boiler. In the boiler, if you remember, we said that we have constant pressure heat addition. So you can select in the pressure part, you can select pressure drop correlation. Since the pressure is constant, the pressure drop is 0. This is the best or easiest option when it comes to adding information about the boiler and the condenser. I will show you later why. And we know that the output temperature of the boiler is 600 degrees C. We see the blue check, we are done, we move on. Then we have the condenser. In the condenser, the information that we have is that the pressure drop is 0 because we have constant pressure. And you can either select the temperature or other options. I go for vapor fraction. When you select vapor fraction, you specify the vapor fraction here. If I put 1, it means that the output of the condenser is saturated vapor. If I put 0, it's saturated liquid. And since in our design it should be saturated liquid because it enters the pump, so we just simply put 0 here. So the program assumes that the output of the condenser should be saturated liquid. You can also make sub cooled water here if you want, but this is enough for now, and we are dealing for ideal case. So we move on to the next section is the pump. The model should be pump. The discharge pressure of the pump is the same as the pressure of the boiler, so is 15, and it is megapascal. So we are done. If you have information about the efficiency for the pump itself and its driver, you can input information here. For instance, if you have like 80% uh, efficiency, you put 0.8 here. So we proceed. Then we have the turbine. So you need to model it with the turbine model. Then the type of the turbine you can select here. We assume that it's isentropic. Uh, so you need to specify the discharge pressure if you want. We said that the condenser pressure is 10 kilopascal. So the steam that goes out from the uh, turbine goes directly to the condenser, and we have constant pressure here, right? So if the pressure in condenser is 10 kilopascal, so the discharge pressure of the turbine should be 10 kilopascal. So we change bar to kilopascal here, and isentropic efficiency, I leave it empty. If you have a number, you put the values here. So we are done. If you click on the next, a message appears here that the required input is completed, and you can move on to do the simulation. We press on OK to proceed with the simulation. So, so we press on OK and then wait for the program to perform the simulation. Now the simulation is over. It says results available with error down here. When you see this red error message, it means that you have an error in your simulation, so we can check the control panel in order to find the error message. So here you see that the error occurs in turbine block. It says that the liquid phase exists either at the outlet condition or at some intermediate condition. You need to specify valid phases. So we go back to the main flow sheet. You see this red cross here. So the problem is somewhere in turbine. So we double click on the turbine. You go to the convergence. So here the valid phase for the flash calculation is vapor only, and we, since the pressure is 10 kilopascal, it might happen that we have some liquid in the output of the turbine. So we change this to vapor liquid. Now we reset uh, simulation in order to purge all the results. Uh, and then we rerun the simulation using the next button. This time, after the simulation is finished, you see that it says results available, so you have no error message, so you're safe to proceed and analyze your results. So we go back to the main flow sheet. In order to check the results, you have two alternatives. Alternative one is that you either right click on each stream and you go to results. For instance, the turbine in, you have all the information about enthalpy, entropy, molar density, flow rate, etc. For each block, you do the same. Select, right click, go to results. And here, for instance, you go to the block, you see that the network that is produced is given here. So given the condition that we have in this equation, in this simulation, we have almost minus 3000 kilowatt that is produced as work in the turbine. The other alternative is that you go to this left sidebar, and here you see that you have a list of blocks and a list of streams. So if you go to list of blocks, let's say that we want to check the pump, and here you have a result tab. So here it says that in order to pump the water that you have from the condenser, the brake power or net work that you require is around 100 kilowatts. You can also go to the streams and check the stream results and input from this navigation bar. Uh, there is also one more possibility, and that's in the top here. You can in the flow sheet you can check these boxes. If you check, for instance, temperature, the temperature of each stream appears on top. And if you click on pressure, for instance, vapor fraction, heat and work, you see that they are appearing here on the main flow sheet. So uh, this is a one way that you can see immediately your results. But note that sometimes, I mean, the decimals are small here. You see a zero here, but it's not uh, like a zero. It's like 0.0 something, but you see a zero here. So it's important to double check that. So if I click on, for instance, vapor fraction, you see that you have 97% vapor fraction in the output of the turbine, which means that 97% of your stream here is vapor. And you have 3% liquid, and that's why you got that error, because if you had in the model, flash model, we had only liquid. So we change it to liquid vapor, and uh, this vapor liquid phase is now a valid flash option, and the simulation works properly. In order to calculate the thermal efficiency of the cycle, we need the work that is produced in the turbine. We subtract the work consumed in the pump, and then this is the network, and we divide it by the Q that we need to provide in the boiler. Uh, the If you look here, for instance, the Q for the boiler is given in calorie per second, but the power produced and consumed in the pump and turbine is in kilowatts. So be careful when you do the calculations. The alternative is to ask the Aspen to do the calculations for the efficiency. I will show you in the next video how to use the calculator in the flow sheeting option, we can use the calculator to perform some calculations. See you in the next video.